So for everyone who might not know me, I'm Jonathan. I'm the technical lead for Electromagnetics at EMIT. And so during this presentation, we're looking at updates to HFSS and also to the interference tool with EMIT. And so we kind of get started with splitting the two halves. We're looking at main solver enhancements, so any good things you can sort of use with the software, and then just things which make everything more comfortable. So the first thing you'll notice, this is what you've probably been used to using in HFSS for the last 20-something years, where you have, you specify a frequency you want to solve at, you choose the number of passes, you choose an accuracy, and then you solve from there. We've got about 1 million tabs across the top as features have been added to the software. And this is great for power users in the room who use it every day and do the hand counts to get started. For everyone else, we've got a new auto setup. So it used to be that choosing the meshing frequency was really important and things like that. Now we have a lot of cores available, and particularly with wideband designs, very few people spend a lot of time working out how to do meshing anyway. And so we've kind of taken that off your hands. We now look at how to do the heuristics in the background ourselves. The only thing you supply for your simulation is whether you want to be fast, balanced, or accurate, and what frequency band you're interested in doing. And you choose a sweep as per normal. And all the control that used to be up here, and they're all hidden in the background, and you simply just choose whatever you want from this screen. And so if we look at how this works in practice, this is a transition from a cable into a connector into a PCB in the underline. This is usually a fairly challenging problem to get the adaptive frequency right, because you get all sorts of resonances inside this design. And so if we go and before we look at the speed part, just look at the results. These show you the setting results from all three settings, so fast, balanced, and accurate. And the only place that really any difference at all is this very small region here, and that's about 2 or 3 dB difference. So overall, the answer is almost identical between all the settings. But if we look at how long it took to get them, your high speed ones are 25 minutes and 10 gigs of RAM, and your high accuracy is 52 minutes and 70 gigs of RAM. So to kind of put everyone's fears and suspicions at rest a little bit, there's a very good reason to use the high speed option, particularly when you're first building designs up. So, well worth the play. This is actually what I use about 50% of the time now, whenever I'm not doing optimization work. And so that gives us kind of a recommendation of when you might use either the simpler settings or more advanced ones. We use the simpler settings for almost everything. The only time we don't use them is with very technical optimization work, where we need to minimize things like mesh noise and have very tight control over how the solver works. So that's well worth having play. For everyone who's doing anything to do with platforms, we end up bringing in geometry from all sorts of different sources. Particularly cars is a particularly bad one. We have the option now to let the mesher have a bit more leniency in how it produces things. So it used to be that you'd have the top of the car and you'd put an antenna on top, and then you'd want to mesh the whole car, and somewhere in the bottom where the chassis is, the CAD's got like this. It's all intersecting, it doesn't really work. Previously you'd spend like a week in space cleaning, trying to clean everything up. Now you have the option to come to the mesh settings, choose what we call the flex mesher, and this will then go and walk across all the bad geometry, but it'll give you a warning whenever it does so. So for example, on the car option, if underneath the chassis, you get a warning for a mesh leak, and you go and look at it, and it's miles away from any antennas, just carry on, leave it, it'll be fine. So this is a huge improvement for the platform studies. We go from we've done projects where it's been a 5-hour initial mesh generation. Now it takes about 20 minutes. So this is all the 33 test models from ANSYS, and all of them are roughly twice as fast or a little bit more. So this is a fairly enormous saving in terms of not only workflow, but also the solve time. So anyone who's doing particularly radar, especially for autonomous vehicles, it used to be that you'd spend about 20 minutes in Excel working out how to set all your frequency sweeps based on the data sheet. That's kind of been turned on its head in R2, and what we option now is you can switch it from standard to range Doppler. It turns this window basically on its head, and now you type in just whatever you see on the data sheet, and HFSS does the hand calc in the background for you to work out how to set up the simulation for frequency sweeping and things like that. The other thing that this comes with is a new solver modification in the background And before I show you how it works, it requires both the HFSS and the SPR Plus licenses. But in essence, what it does is, this used to be a really big achievement. Getting this level of detail, the arranged Doppler plot, was pretty impressive because it takes 288,000 frequency calculations to produce this plot. So that's all well and good, but this was definitely the case if you buy a high-end solve box to produce it. With R2, we now have a special modification for whenever we move this vehicle through the scene, we use a lot less rays to produce it. It reuses them a lot and things like that. But in essence, now it's almost 100 times faster. So this went from being a very big achievement to fairly basic, 20 minutes on a laptop. And now we have the option to do stuff like this. So this was almost 300,000 frequency sweeps. This is 23 million frequency sweeps. And this solves in 2 hours on a laptop. So we can produce very, very detailed range Doppler plots now with not very much computation. If we look at the side effect of sticking this antenna on the front of the car platform, we used to have the problem where you would take your antenna to HFSS, you put a huge in the box around the outside, you extract the current vectors on that box, and that becomes the source for your ray tracing, so your SPR Plus simulation. When you went to mount that on a platform, so say the front fascia of a car, you'd find that you could never quite get the bottom of this to line up properly with the nearest bit of bodywork. And so you'd get the, please move the antenna to more than 1/50 lambda away from the surface area, which is very, very frustrating to solve. Now you have the option to come and turn on what we call current performance. And so in essence, there is this gap here. HFSS sees it as a gap, moves along, looks at the top couple of layers of current elements, and extrapolates down to the surface so that you end up with a perfect zero gap here, and you never ever get that error again. So that's very, very easy to get sorted. The other thing to be wary of is if you're going to do this with a conducting surface, try and add a ground plane to your original HFSS design to sort out the ground clearance. The other option you get as part of this workflow is when you use to sample the Huygens box, you get a lot of current sources which didn't do very much. And so if you were to go and look for all the small blue ones, then you'd end up with sort of 100 of them which did a lot, and then 1,000 of them which didn't really do anything. And so you now have the option to simplify it down, so you can choose thin sources and a fraction, and we'll throw away anything which doesn't contribute. So for all intents and purposes, these two are identical, except this one solves about 30 times faster than that one. So that's another very big speed up for platform. If anyone's been using the brand new feature for doing radar cross sections with the SPR Plus solver, we now have the option to use creeping waves. And so the scenario where you might use that is this is the new R1&R2 heavy lift configuration. And if we were to shoot a radar pulse down onto the surface of the vehicle, the SPR Plus solver paints all over this top line, so you'll see lots of rays intersecting with it. Once it gets to this black line though, it can no longer see the backside of the conductor, in which case it can't see it, and that gives you a false radar return. And so if you go and add the ability to carry on the energy, so it doesn't no longer see the high impedance along this black line, the way we do it is we use what's called creeping wave. And so whenever we get to the black line, SPR Plus launches rays which can travel around the curved surface, and then if it's the right radius, they'll come right back around and re-emit. And so if we look at a simple test case of a sphere, this is the strong main return that you see. This is caused by rays intersecting with the front flat surface. If you don't have creeping wave turned on, the rays stop being seen past this line here, and then this high impedance causes an additional reflection. And so you see this line here. And this isn't real. If you go and measure it in real life, you don't see that. And the reason for it is you need to add the creeping wave so that currents can go at the back of the sphere and then re-emit coming forward. So this is the artifact, and then this is the actual return you get from those creeping waves. Another enhancement to the SPR Plus solver is previously when you've used a Phoebe region as a source for the overall antenna, what we used to find is that the rays get emitted by the source, they intersect with the dish, and then when they come back, they don't see this region, because the SBR Plus is like a one-way code. So that means that if you're looking at the overall performance of the antenna, it's okay down the main beam, but there are certain parts of the side lobes which didn't quite get handled properly, because they're caused by reflections with the feeding source. And so now you can open up this component, and you have the option to choose which parts of this component act and respond to the SBR Plus rays. And so you have the options to either block them as a perfect absorber or as a perfect reflector. But if we look at the results that we get for that, then we see, if we look on the radiation pattern, the blue line is the old SBR Plus without the blockage. The green line is the full hybrid feeding simulation, and you can see that your side lobes are now correctly being balanced out because those rays are no longer not seeing the source. So they give you the correct reflections. But you still get the same speed and RAM requirements that you usually expect with the SBR Plus. Particularly for people dealing with paintwork, it's very hard to work out what the reflective properties of paint would look like, and manufacturers won't give them to you because they don't really know either. So what you can do now is if you take a sample and you measure its reflections at a number of different angles, you can import that data as a Fresnel table, which looks like a bunch of real and imaginary components versus frequency and angle. Previously, if you tried to get either air or PEC, you couldn't get a correlation between what the actual material would be. So with adding that table, you now can approximate it more accurately. It's still not quite perfect, but you can load in the external file from there, and that gives you a new boundary condition. For anyone who's been doing very, very large hybrid solves, so in this case we have a very large automotive radar antenna and a very small receiving one here. If you tried to solve both that and the front of the car, it would take a very long time because you not only solve this one in detail, but you solve this part in detail too. And this one doesn't really contribute all that much beyond the basic mesh. And so what we can do now is you can tell it to skip the IE region, which is this part here, adapt through this one till it's accurate, and then it will swap back and include both of them for the final calculation. So if we look at what that looks like in practice, the radiation pattern's almost identical, except that now instead of taking 62 hours to solve, it takes just under 6 hours. So that is purely by cutting out the extra IE solve. So there's a lot of general things. So our IE solver hasn't had a lot of love over the last 2 releases, but particularly for scenarios like this, where we have closely spaced antennas on a flat surface, these elements at the bottom used to cause a lot of issues and slow the solver down. So now with a few extra enhancements, both of our solvers are quite dramatically faster, 50% for the ACA, which is the one used for very complicated surfaces, and 300% for the MLFNM solver, which is used for very big, simple ones. This is a brand new solver for use in HFSS. If anyone's doing anything where you might have high RF power, plus usually a vacuum, you have this effect which can occur called multipaction. It's a quantum effect, and it's inherently transient in nature, and it's caused by electrons being knocked out of a conductive surface and then finding their way to another conductor. If they have enough energy, which is usually when you have a very high-powered RF field, they can cause a cascade, and so this one electron will knock out more than one here, bounce back and forth, cascades, produces an arc. The next part of the experience for your device will either be exploding, catching fire, or melting in some description. So we now have the option to you calculate a frequency sweep, as you otherwise would, and you add the multipaction option onto that frequency sweep, and that runs a small transient solver in the background, almost like a post-processor. But it has to be transient because it's nonlinear and quantum in nature. And you specify regions where you'd like to do it. And so this is what it looks like in practice. Right-clicking the sweep, add the option, choose which carriers you'd like to look at. So if you're exciting multiple carriers in a given device, then you can add both of them in. And then it runs a couple of different levels of power automatically. And the reason for that is we'd like to look at which point is the trip over point, where you start getting cascade occurring. So This is one with no multi-paction treatment to the system. You've got 2 power levels at 500 and 1000, which don't trip over and cascade. But above 1000, at 3 to 4000, we get a dramatic failure, and it's over the course of nanoseconds. If we were to go back to this one here, and if we pass a DC current down the center, that twists the magnetic fields around, and we can deflect those electrons from getting to the center. And so if we run another analysis, you'll see that these 2 high-powered options now don't quite get enough energy in order to cascade through the rest of the system. So if we look at purely GUI workflow, this is usually where you save most of your time. The first thing people usually ask about is what can we do with the ANSYS cloud? And so as of tomorrow, we can now use ANSYS HFSS and SI Wave as part of a cloud solve. We have pre-configured node options, so this saves you all the time usually if you've ever used AWS or something where you've got to create an instance, set up storage, load the right image with ANSYS installed, set up licensing, and all that kind of stuff. Basically what happens is you set up your solve in Electromagnetics desktop, you go to what used to be thought of as just the cluster scheduler tool, and you choose ANSYS Cloud instead of a cluster, and then you log in, and that gives you access to your elastic compute unit. Then you push launch, and it submits it to the queue, and then it solves automatically in the cloud. You can watch it converge and see all the normal post-processing stuff that you would get. You can do it on your phone if you're bored. When you're finished, you have the options to either download partial or all the results. And so this is very good for if you're doing platform type work and you just want to see the radiation pattern and the S parameters, then you can download just those results back to HFSS. And you don't have to download the 60 gigabytes of extra field data that go along with it. So it's quite a nice workflow. If you've been using ANSYS EMIT, particularly in a standalone GUI, and you've always wanted to be able to take HFSS projects straight into EMIT, now we've kind of turned the idea on its head a little bit, and we can take the EMIT GUI and put it as a beta feature inside the Electromagnetics desktop. So where you would usually, you could insert an HFSS design, there's a new option for insert EMIT. It gives you access to the same GUI you're expecting inside the interference tool. It's currently locked down in the window arrangement, but that'll get changed soon. All the components are integrated into the tree as the rest of things in Electromagnetics desktop. And there's a couple of extra new features available which you didn't used to be able to have. One of them is dynamic links to HFSS. So if you've been moving your antennas around to try and improve interference, rather than always having to re-export files all the time, you can now set up a dynamic link when you update the HFSS part. It automatically updates the EMIT part as well. So that's a nice improvement to that workflow. For anyone who's ever doing EMC work, particularly in vehicles, it used to be a fairly convoluted process. You would spend a bit of time working out what your cables look like, you'd spend time working out what your excitations look like, so you might model some power electronics, you might do a lot of semiconductor work, some conductors, to get the right content to excite the model with. And the final step would be you take the cable into HFSS, solve the whole thing, realize you stuffed up, come all the way back to the start, and change the circuit again. And so a very long process to get to the final answer. Now the way we do it now is we break the process in the middle. You can take your cable into HFSS as per normal, but then you, rather than always having to look at the circuit, you just have ports connected to excitations like this. And so you can now do whatever you like in the circuit world, export a new set of excitations, frequency dependent, load them into the circuit, excite the last mesh you created in HFSS, and we'll re-update everything in one go. No more having to resolve the huge process all over again. For everyone doing PCBs, particularly in HFSS 3D layout, so it used to be that the worlds of mechanical and PCBs were quite separated. It was hard to solve both at the same time. Now you have the option to do what we call full assembly, and so you can solve a 3D layout problem with all your ports and import your ECAD and do the stack up. But when you want to do the final assessment, you can drag and drop an HFSS design straight into it. So if you've got a connector with some ports already set on both ends, when you drag them into this view, if it sees there are pads already lined up, it automatically aligns the ports and sets up the linking for you. So that means you can drag in other things too, like the chassis, and this gives you a full design like that. And in the background, you'll find that all the parts that were associated with PCBs now use all the PCB solver configuration, including fire mesher, and everything that wasn't a mechanical interface swaps over to use the classic. So you get the best of both worlds without having to endure using classic with PCBs or struggle to get PCBs to work with components. So that's very nice and efficient. Carrying on with the PCB idea, when we load in 3D components, you find that there's so much information stored and there's a lot of connections going on where HFSS comes along and checks every single hole in the pads to make sure they're not overlapping with the trace. Now what it will do is it cuts out half the data. It still has the same checks, but they're 3 to 4 times faster in most cases. In a few validation cases where we have lots of issues, going from last year's release to this year's, we go from 24 hours of validation down to 10 minutes. So there are a few bottlenecks which have been cut straight out of that workflow. And my last slide is to anyone who's been using optimization heavily inside Electronics Desktop. Previously, you've had access to 1 or 2 gradients, a generic optimizer, and 1 or 2 nonlinear sequential optimizers. They're a bit limited in what you can do with a lot of things, but now you've got the extra options to use the Design Explorer ones. So in particular, you've got the screening one and the multi-objective genetics. These are good for doing performance envelope type work. So you can add them as you always did. They're down the bottom of the list. You click go, and then they fire up the algorithms which were previously inside DX.